Okay, thank you very much. My name is Hidenori Fukaya. I came from Osaka. It is a great pleasure to give a talk face-to-face. So let me thank the organizers, especially Yasumichi-san, for inviting me to this nice workshop. This talk is based on the work in chiral QCD collaboration, including these members. This project was and is supported by many computational resources, including Fugaku. So let me also acknowledge these supercomputers. In this talk, I'd like to address the QCD phase transition, which occurred at around 150 MeV temperature, or 10 microseconds after the Big Bang, where the SU2 cross SU2 chiral symmetry was spontaneously broken down. The phase transition is proved usually by the chiral condensate, which is the first derivative of the log of the QCD partition function, or chiral susceptibility, which is the second derivative with respect to the Cook mass. In this talk, we focus on this chiral susceptibility. And we treat the only two flavor balance quark, where the strange quark is treated just as a spectator. Let me illustrate what happens in the chiral phase transition. At some critical temperature Tc, in the standard second order scenario, chiral condensate drops to 0. But this happens only in the exactly massless case. And for massive case, the transition becomes milder to be a crossover like this. So it is important to look at the quark mass dependence of the chiral condensate at fixed temperatures like this. For example, for lower temperatures, the condensate is always non-zero, perhaps slightly decreasing towards the chiral limit, but it convergent to non-zero values. But for higher temperature, we should have a sharp drop near the chiral limit to 0. And this drop should be reflected as the peaks in the chiral susceptibility, because we take the derivative of this with respect to the quark mass. So it is the standard scenario of the chiral phase transition, and we will investigate this chiral susceptibility, including this peak behavior. When the transition is first order, in this case, we should have a discrete jump to 0 of the chiral condensate. But on the lattice, the finite volume effect would make the transition not very sharp. So the behavior we should see will be similar to the second order case. So anyway, the chiral condensate proves the SU2 cross SU2 symmetry breaking or restoration. For temperature below Tc, condensate is non-zero. For above Tc, it becomes 0 in the chiral limit. But this Q/Q operator also breaks the actual U1 symmetry. And my question in this talk is how much does this U1 anomaly or yuan breaking contribute to the transition. You may think that the temperature and the mass dependence of the chiral condensate should be should reflect only the SU2 cross SU2 breaking, because the anomaly exists at any energy scale at energy temperature, and we don't expect it does not change very much. So some schematically, we can imagine the breaking effect like this. Your anomaly always exists at any mass and at any temperature. So the non-trivial temperature dependence and the mass dependence should reflect the SU2 cross SU2 breaking. But in early days of QCD, QCD founders in 70s or 80s thought differently, because they thought that the instanton may describe the everything of the QCD low energy dynamics. And in a paper by Carandash and Gross, they proposed and actually computed the instanton enhances the actual U anomaly, and this is the trigger of the SU2 cross SU2 breaking. So if this and this inverses are true, we may see that instanton disappearing, which suppress the anomaly, which is a trigger of the SU2 cross SU2 restoration. But this issue has been difficult, and we do not know the answer yet. On analytical side, the semi-classical QCD instantons are not enough to describe the low energy dynamics of QCD. On the lattice, in the previous works, they employed the fermion action explicitly break the chiral symmetry. Moreover, in our previous study, that we found that the lattice artifacts, especially on the actually U1 related quantities, are enhanced at a high temperature. So in this work, we employ the exactly chiral symmetric Dirac operator to study the chiral condensate and its susceptibility in 2 and 2+1 flavor QCD. Our method enables us to separate the actual U1 breaking part, in particular topological effect, from others in a theoretically clean way. And we will see that our result shows that the signal of chiral susceptibility is governed by the actual U1 breaking effect, in fact, rather than SU2 cross SU2. Okay, this is the introduction of my talk, where we simulate the chiral phase transition of QCD with exactly chiral symmetric Dirac operator to investigate, to clarify the role of actually U anomaly at the transition. Next, I'd like to explain let me explain how to separate the actual U1 anomaly contribution to the chiral susceptibility. Okay, in this work, we treat the quark determinant by the products of eigenvalues of the Dirac operator. So that the chiral condensate, is given by the summation of the configuration of this, configuration average of this summation over the eigenvalues. And the chiral susceptibility is decomposed into a connected part, which is the derivative of the condensate with respect to the valence Cook mass, and this connected part, the derivative with respect to the C Cook mass. And we note that the scalar and the pseudo-scalar isospin singlet operators and the isospin triplet operators are related by the SU2 cross SU2 and axial U1 rotations with angle pi. Using this, the chiral susceptibility is given by the scalar susceptibility by definition. And we can also include the theta vacuum effect and performing the chiral rotation. We can relate the topological susceptibility to the pseudo-scalar correlators, pseudo-scalar susceptibility. And we can also use the Ward-Takahashi identity of the, for example, pseudo-scalar triplet operator to have this non-trivial relation. And we can now express this chiral susceptibility in terms of these many susceptibilities as well as topological susceptibility. And it's a rather messy slide, but we can decompose the connected part of the susceptibility and the disconnected part into these susceptibilities, which are non-perturbative relations. Okay, to separate the axial U1 breaking contribution in red characters and that for SU2 cross SU2 breaking with blue colors and some mixed contribution. Here delta U1 denotes the so-called axial U1 susceptibility, which is given by the difference of pion and the delta meson correlators averaged over space-time. And delta SU21 and delta SU2 are difference between sigma meson and pion and delta meson and eta prime. Okay, so far we have written everything in continuum notation, but on the lattice we use the eigenvalues of the massive overlap Dirac operator, like this. And I have two remarks here. In these quantities, we don't have any eigenfunction dependence. So these quantities are all written by the eigenvalues of Dirac operator only. Second remark is that to obtain these formulas, the exact chiral symmetry is essential in the massless limit. Okay, we have shown that U1 contribution to the chiral susceptibility can be separated. Okay, let me explain our simulation setup. We simulated two flavor QCD at lattice spacing 0.075 centimeter on 4 different volume size. We employ semantic gauge action and Möbius domain Hall fermions for the configuration generation with residual mass less than 1 MeV. And we reweight the configuration to by the overlap determinant, overlap fermion determinant. And our quark mass covers the point below the physical point. And our simulated temperatures are 5 temperatures tuning by the temporal extent of the lattice. This is a simulation setup, preliminary simulation of 2+1 flavor QCD, where we use the cutoff around 2.45 GeV, and the lattice size is 2.6 centimeter, and the up-down quark mass covers the physical point. Okay, what is the difference between overlap and the Möbius domain Hall? Overlap Dirac operator is a kind of perfect chiral symmetric Dirac operator. And domain Hall, 4-dimensional effective domain Hall Dirac operator is just an approximation of this. But numerically, in our work, we call overlap if the residual mass is around keV, and we call domain Hall when the residual mass is around 1 MeV. Okay, we need this reweighting because we found that Ginsburg-Wilson relation is strongly violated at some eigenvalues of domain Hall Dirac operator, especially above critical temperature. So we decided to perform the overlap domain Hall reweighting, where the reweighting factor of the ratio of the determinant is stochastically computed. Here we have a bonus of topology tunnelings. It is known that if you stick to overlap fermion in the hybrid Monte Carlo simulation, we need to fix topology. Otherwise, the Monte Carlo simulation will stuck. But for this reweighting technique, we can allow topology tunnelings. Thank you. Okay. In the eigenvalue summations, we have to truncate at some cutoff. And we truncate, our truncation scale is around 150 or 300 MeV, depending on parameters. And we check the saturation comparing with the direct inversion of the Möbius domain Hall fermion. And for lower temperature, we find a good saturation and consistency with the direct inversion of the domain Hall Dirac operator. But our highest temperature shows some deviation. So for this temperature, we use the direct inversion of the Möbius domain Hall. Okay, let me show you the results. These figures are result at a temperature around 220 MeV, where we plotted the quark mass dependence of the connected susceptibility on the left-hand panel and the disconnected part on the right. And the colored magenta open squares are the total contribution of the chiral susceptibility, and the black dashed symbols are those from U1 breaking contribution only. So you can see that the signals are almost dominated by the actual U1 breaking effect. For the connected part, it's dominated by the U1 susceptibility, and the disconnected part is dominated by topological susceptibility. Okay, the dominance by this actual U1 breaking effect is seen at 5 different temperatures. So colored symbols are total contributions. Again, the left panel shows the connected part and the right panel shows the disconnected part. And the colored symbols are almost dominated by these black symbols, proving the only actual U1 breaking part. Okay, in fact, say 90% of the signal is from actual U1 anomaly. Okay. We also see this dominance in 2+1 preliminary results, but the signals are still noisy to identify the peaks. Okay, there's an interesting report from double hot QCD collaboration where they used the Wilson fermion to simulate the high temperature QCD, and they reported that this connected susceptibility and topological susceptibility are very much correlated, which is consistent with our results. Okay, but I have to confess that there is a subtlety in the when you sum up the connected part and the disconnected part. Actually, we see a large cancellation between this U1 susceptibility and the topological susceptibility divided by clock mass square. And in total contribution, this single contribution from chiral zero mode dominates the signal. But this term is expected to vanish in the large volume limit. So it is difficult to tell what survives really in the total contribution in the large volume limit. Yeah. Okay. Let me summarize my talk. We simulate 2 flavor and 2+1 flavor lattice QCD. And the chiral condensate and susceptibility are related to both, not only to SU2 cross SU2, but to actually U1 symmetry. In the spectral decomposition of the Dirac operator, where if you have an exact chiral symmetry, we can separate the purely U1 anomaly effect. The connected and the disconnected susceptibilities are each dominated by the actual U1 breaking effect at temperature above critical temperature. So our data would suggest that the actual U1 anomaly may play more important role in the phase transition than expected. So take home message is that chiral susceptibility is proving not only SU2 cross SU2, but also actual U1 anomaly. Actually our data shows that the signal of the chiral susceptibility is dominated by the actual U1 anomaly. That's all. Thank you very much.